Hello and welcome to our BayesiaLab webinar. Thank you for joining us today. Today we'll talk about the fallacy of single point forecast, and in this context we'll introduce the BayesiaLab WebSimulator. My name is Stefan Conradi and I'm the managing partner of Bayesian USA, and I will be taking you through today's program. So, we'll start off by talking about our motivation. That is, our motivation is the fallacy of single point forecast and what challenges this produces. It is really our objective how we can, or we want to figure out how we can overcome these challenges. And that would be, we want to pursue communicating distributions to stakeholders. We want to allow stakeholders to independently simulate and evaluate scenarios in the business case that we're going to explore. And the specific business case that we're going to look at is about inventory and capacity planning based on forecast, on assumptions about the world, about consumers, about demand, etc. Continuing in our agenda today, and actually before I continue, I should mention this introductory part should take approximately 20 minutes or so. Then continuing on, there we're going into our actual workflow. We'll start off inside BayesiaLab. We'll create a Bayesian network model to represent our business case. We will use that model to search for an optimal solution, in this case looking for an optimal capacity or inventory, and based on that we will develop a web simulator or design its appearance so that end users, stakeholders who don't have BayesiaLab can utilize this model and simulate their own scenarios. Now then we'll switch into the web simulator from a desktop-based software to the web, to a web application. We will upload the Bayesian network model that we just built. Then we can simulate conditions again. We can import any predefined scenarios that we may have, etc. So that part should take approximately 40 minutes. So just to give you a sense of where this belongs in the ecosystem of BayesiaLab, so BayesiaLab is obviously a desktop-based software that you will see running on my computer here today. And then we will also show BayesiaLab WebSimulator. That's our web application in this context. And as we go through the example and the case study, you may see several new features of, well, not new features in BayesiaLab, but perhaps new to you, such as decision nodes, utility nodes, equations, scenarios. And then here's actually something new, and that is we can now be a lot more differentiated in the way how nodes appear in BayesiaLab. We can show monitors directly on nodes. Those were some of the things that were introduced with BayesiaLab version 8. One thing I should say before we move before we begin properly, all the slides, all the networks that you'll see today will be available for download, and if the recording works out, you will also be able to watch a video of this program today. So let's start off with our motivation, the fallacy of single point forecasts. And perhaps many of you are familiar with the situation in the corporate world. I've certainly been in it many times. To make decisions, executives need estimates from their team members, whether it be investment decisions, product decisions, marketing decisions, and typically the team members provide their forecasts in the form of single point estimates. They may forecast daily sales, marketing expenses, anticipated budgets, anticipated costs, and everybody brings in their number. They bring in their single point forecast, and then all these individual forecasts go into the world's largest spreadsheets as a single number. and then out comes at the bottom, let's say a net present value or a profit, upon which a decision is made. So we've got all these individual numbers, these individual points that go in, and a single number comes out. I'm not exaggerating. I know this from my own experience in several different industries. So what's the problem here? What is the challenge with that? The problem is even if such a single point forecast is correct on average, the problem is that if we have this value, let's say we are expecting to sell 8 units a day, on that value we can certainly make an optimal decision. We can plan for that. But the reality looks more like this, that we have a distribution of daily sales, that not every day we sell exactly 8 units. So even though the distribution may have the exact same expected value as the single point forecast, the optimal decision for the distribution may not be the same. It may be quite different than for the single point value. So that is the challenge. So what we need to do here, or what this task is really all about, is that we stop with the single point forecast nonsense and really work consistently in our models with distribution. So that is absolutely mandatory. And so not just distributions in the terms of a little bit of a fudge factor here or there, but being very, very explicit about what we have, what we assume, what our degree of certainty is. We want to spell it out. And in that context, Bayesian networks are extremely, extremely useful because we can work explicitly with distributions. Bayesian networks are very, very transparent. So all assumptions, calculations are very transparent. Anybody can look inside and see what is happening. We can look at the distributions of every single variable, so we can get a very good sense of what is happening, what we're simulating. So we're getting away from these black box models that are often these gigantic spreadsheets where it's often even difficult to track down an error because the relationships are all hidden in, complicated formulas that link multiple tables and tabs and so on. So that's our objective, to be explicit. Now, to illustrate our approach, we'll share with you a very, very simplified example. So I should need to add that as a caveat. Because you may laugh about some of the simplistic assumptions that we make for this fictional business, the fictional business plan we're about to propose. So this is what we want to do. We want to start a new business or new business division for which we need to plan inventory or capacity. And this is a generic business, could really represent anything from a car rental station to a hotel to a new airline route, something where we have to deal with, units that we need to keep available for a customer demand. And again, this is very generic, and not all facets of the problem equally apply to airlines and hotels and so on. But it's all about having the right inventory, having the right capacity for customer demand. So beyond demand, which we obviously need to estimate and assume, there are several other assumptions that we may need to make, such as the profit that we would make per unit sold or rented. Also, the cost per unsold unit. So if we, hold an empty hotel room or fly an empty airline seat through the air, that's a cost to us. And then perhaps a potential bigger cost could be what happens if we can't provide the service or the product to a customer who has reserved it. Perhaps you're familiar with it when you get bumped off a flight, when an airline oversold its available seat. So that obviously is a cost, because then you have to be reaccommodated, typically at a fairly high cost. Now, what I should mention here that we're talking about a new business, so we don't have any existing data. So whereas for other examples we have used historical data to machine learn a model, here we're just thinking about our assumptions and putting them together. Now, I went through this presentation earlier this morning, and I wanted to offer kind of an extra twist, something interesting to make the example a little more realistic. And I thought, well, perhaps we can look at a business case where we offer two classes of service, like economy and first, base versus premium. We'll probably not have time to go through this particular twist in the model, which certainly makes it a lot more interesting and realistic. However, I will share a model that includes that, so you'll be able to download that later and experiment with that yourself, and then figure out whether the solution that you may have guessed is in fact the ideal solution given specific demands. So these are the typical questions we want to answer in the context of our business case development. Such as, given the demand forecast and other business assumptions, what is the optimal capacity or inventory level? And here I'm using capacity inventory exchangeably. Again, this is a very generic business case. And given any uncertainty in forecasts that we capture in distributions, how should the target capacity be adjusted? So how does the uncertainty that we have in forecasts, how do we reflect that, and what is the optimal capacity for planning purposes? So this is what we're going to do. We will model our knowledge, we'll model our business case, which is really a type of expert knowledge modeling. That gives us a Bayesian network, and once we have that Bayesian network, we can simulate with that, we can look for optimal solutions, etc. So, and of course, all of that we will do in BayesiaLab 8. You may have seen BayesiaLab in other contexts, especially for machine learning Bayesian networks, but today we're purely using it for encoding and our knowledge and then simulating with it. So here is the workflow more specifically. We will encode the business model, then provide very specific assumptions or a range of assumptions, different scenarios. We will use policy learning to find optimal capacity levels. And then really this is perhaps the most interesting part. Then we will design a web simulator so the model that we have developed, others can use. Anybody with web access can utilize that model and try out their own scenarios. So that part we will do in the web simulator. So, but let's start with our business model. It's really quite straightforward. We'll start with the core. I would argue that the number of units that we can sell is a function of both the capacity that we have and the demand, the consumer demand. And so here, as this is being set up as a Bayesian network, units sold has two parent nodes, capacity and demand. Now, typically, as we set up Bayesian networks, we would now generate a conditional probability table and fill out that table either with our domain knowledge or we would learn that from data. Here, however, what we're going to do is we will enter a deterministic equation in the node editor. This is quite practical in those cases when there is in fact a logical, a deterministic relationship between nodes. So here in this case, it's a very simple if-then statement. You know, if the capacity is greater than demand, then actually the demand is the actual number of sales we can make, etc. Very straightforward. Now, this is probably how you typically see conditional probability tables, or rather what's behind a node. But I should point out that even though we've entered an equation here, or an if-then statement, A Bayesian network is entirely, or in BayesiaLab, a Bayesian network is entirely non-parametric. So this equation is being translated into a conditional probability table in the background. So that's the way that logic is represented in BayesiaLab, and that's how inference is being performed. As I said, in other contexts, we might have filled out this table directly, or more commonly, we would have machine learned that table from data. So let's continue our business model. Let's now add another node. This is on the bottom left here, surplus and shortage. This is now the node that captures how many units we have too many or how many units we are short. And that can have major implications, as you can imagine, if we have customers who've made a reservation to whom we can't deliver the product, or in this most often where we have to deny them an airline seat and then re-accommodate them. So this node, surplus and shortage, that simply represents the units, too few, too many. And now, of course, we need to assign a cost. And in BayesiaLab, we have the concept of utility nodes that allow us to assign specific values that are associated with states of nodes. And perhaps if we have one seed too many, that has a different cost than being one seed short, and so on. Now we can do the same thing for the units sold, how much profit we generate or revenue we generate. Now there's something very attractive about utility nodes, and that is I can have very many utility nodes in my network, and they all get added up, and so I don't have to specifically link them up. Basically all of them are connected to the bottom line, which keeps your Bayesian network very nice and clean, so you don't need to draw all arcs all over the place. Wherever we have a cost, that is being captured. So this is what we have so far, our model. And now, when looking at these nodes, they have different roles. So demand, for instance, that's an assumption. That's what we have to guess, where we have to rely on a forecast, as opposed to capacity. That would be a decision that we have to make. We have to say, well, we have in our rental car fleet, we have 10 units. Then surplus and shortage are mere calculations. You saw how we entered the formulas earlier. And then cost and profit, they too are calculations. Now we want to make this a little bit more interesting in the sense that let's also make assumptions for the cost, because perhaps that is not constant, or perhaps there is some uncertainty. So we can add further parent nodes to cost, such as cost per unsold unit or cost per oversold unit. That's the unfulfilled demand. So we can, and as you can imagine, we could add more and more parent nodes all over the place, but I'll just leave it at that for at least for cost. And then I'm going to throw in another twist, and we can be as creative as we like, whatever we think is important to capture in a problem domain. Here I'm saying, well, profit is not fixed either. Rather, perhaps that profit is a function of how many units we have in excess, or how few we have. Obviously, thinking that the fewer units we have, or if there's a shortage, then perhaps prices go up and we can be more profitable. Obviously, there are many more dynamics that we could capture here, but I'll leave it at that. So, but again, back to assumption of demand and the decision of how many units to plan. Now, and here I now want to get very specifically into distributions, because the demand, as I said earlier, or as I tried to justify, shouldn't be a single number, but is more likely a distribution. And then perhaps for cost per unsold unit, cost per oversold unit, that's not a fixed assumption either, but rather that can vary as well. And even for decision where we think we can decide how many units we have, but sometimes that gets influenced by external factors as well. Let's say we're a car rental agency, we're planning on having 8 units, but then perhaps customers keep their rental longer or return it earlier, or we get inventory from another station through one-way rental. So even though we're planning to have 8, it may vary. So now we want to figure out how we can conveniently handle that in our model. So what we're going to do is these distributions that I'm talking about, we're going to generate them. And even though we don't have to use this particular approach, we're going to use that because looking at distributions, especially normal distributions in terms of mean and standard deviation, those are fairly common concepts, and even non-statisticians, just business executives, can relate to those. And so therefore we can perhaps capture the distribution as a function of those two measures. But what is very important here is we don't have to. So we could use entirely arbitrary distributions for our assumptions, as you see in this little box on the bottom left. So any arbitrary values that we have, if that's what we think it happens, a bimodal distribution, either demand is very high or very low, but nothing in the middle, we could enter that directly, very conveniently in a Bayesian network. But for our simulator building, as we're working towards an interface for the business decision makers, there we basically just want to give them fewer levers like mean and standard deviation. So let's now put this into our model. So I'm now shifting our model down, and let's look at the upper right hand part here. So now there I have created a node for demand forecast and demand forecast uncertainty. And I'm very casual here about using uncertainty, variation, variance, standard deviation, and so on. And one could be much more precise. Conceptually, they all relate to the same thing, that we have a distribution around the true value. So anyway, so here our decision makers, our business stakeholders need to provide their estimates, and then from these beliefs we compute a demand. And once again we're going to use a formula, but now we're going to use a probabilistic equation in BayesiaLab. That is very helpful because we can simply use the mean and the standard deviation as defined by the parent node, and then compute or rather generate the distribution. But what's important again, in the background, BayesiaLab translates that into a conditional probability table. So we don't calculate with that distribution. As I said, and I will probably say it again, a Bayesian network is non-parametric. We can use this formula simply to populate the conditional probability table. And if we change the formula, we can repopulate it again, but it's the conditional probability table that's behind each node that produces the computations. So that's our demand node. Now, let's now talk about our decision node. And as I said earlier, the decision node, even though the inventory level is something that we can choose and determine, there are external factors. You know, people bring their car back too soon or hold on to it longer. So there we have a distribution. So in this case, for capacity, there's one node that we, or rather one parent node, inventory target, that we choose, And then for the other one, we have to make an assumption. How much variation do we have? Okay, so with that, we have our simplistic business model. And what we now want to do is basically link that up to a control panel so that we can connect all our assumptions into a control panel where we can basically dial in what we believe, where we can set our decisions, what we think, what we should do, and then have an output that computes what is the overall utility, what is the, let's say, the net present value or the overall profit. Now, the way we're going to use that, first, we will do that inside BayesiaLab. So BayesiaLab has kind of its built-in control panel, the monitor panel, where we can immediately do that once we've built the network. And then later, we will transfer to the BayesiaLab WebSimulator. So you can then offer that control panel to anybody to whom you want to make it available via the web. Okay, let's switch to BayesiaLab. Now whereas previously you just saw the graph of the network on a PowerPoint slide, now you see the graph inside BayesiaLab. As we develop the network, we would do that in the modeling mode, and you currently see the modeling mode active. Now to evaluate and simulate, we need to switch into the validation mode, which brings up a new panel on the right, what we call the monitor panel. And in this monitor panel, we can bring up monitors that correspond to each node. So each node that we have here is linked up to a monitor panel. Now that's a lot of arrows here on the screen, but I think you understand how this works. If we had a larger screen, we could also put these monitors, these little bar graphs, directly on top of the node. Sometimes that makes the appearance a little clearer and simpler to use. So anyway, so all our monitors now are on the right-hand side. And what you see here are just some random assumptions that I have entered here. So wherever I clicked on a particular state, I've entered an assumed value. And you see all the assumptions. You see the decision, which is here entered as 5. I've entered the inventory target of 5. And at the bottom, in the purple box, you see the sum of utilities. And so now I can try out different assumptions, and we will do that momentarily live, where we'll then click around and show different possibilities. But for now, I want to show you a few more screenshots of predefined scenarios that I created earlier. For instance, I've created a low uncertainty scenario where basically assumed that the actual fluctuation around the demand and the capacity is very small. So we have very narrow distributions. And based on that scenario, for instance, I could let BayesiaLab learn the optimal policy, figure out which target inventory state gives us the best overall utility. Or I can now do that for what I call a high uncertainty scenario, where I'm a little bit less certain, as indicated by the greater standard deviations that I've specified here. Interestingly here, now our inventory target is a lot higher, even though our demand forecast remains the same. So greater uncertainty in this particular case, given the costs that we have a significant impact on what is the ideal inventory target. Now, we can obviously play with these scenarios and try out different values. And then if we find something that is of interest to us that we think is useful or realistic, we can store that in BayesiaLab. I can save that as an evidence scenario and then share it with other users, even share it with folks who are using this model via a web simulator. So that's a very good way of keeping track of, what different people have assumed, and then perhaps a scenario that ultimately everybody settles on. So, so far this was all in BayesiaLab. Now I want to show you how we can transfer that into a web interface. Again, a few screenshots first, and then I'll make the switch to BayesiaLab, so how we can see how that works live. I have a menu for the web simulator editor where I can assign all kinds of things to my web simulator interface. I can define logos and colors and fonts, titles, and all kinds of things that are relevant to the appearance of my web simulator. And I can define what features, what functions, or rather what nodes I want to show and how I want those nodes to appear. Sometimes there may be certain nodes that I don't want to be manipulated. Certain assumptions that are not relevant to a particular stakeholder, where I say, well, this is built in, this is fixed. So you may not reveal that as an input, but you could show it for reference. Or calculated variables. You don't use them as inputs, but rather show them just as outputs for, well, this is the value, this is the distribution that is contained in a particular node. In this interface, it's very easy with drag and drop. You can add icons, colors, you can size the images to really make that something that is very, very intuitive to use for the end user. And that's really what it's all about. Because the end user is not supposed to be overwhelmed with, with the theory of Bayesian networks, but rather should see this as a model of the business, as a very, very practical model, an intuitive model. So you can almost gain a playful familiarity with this problem domain, and then also recognize whether the model actually represents what perhaps from experience. So that's very, very important, that stakeholders have the ability to kind of compare that to what they have experienced. Perhaps that is a new business, but perhaps they have opened other stations before or other businesses, so perhaps there is familiar domain knowledge available that they can contribute here and compare. So let me briefly talk about the web simulator infrastructure. That's what we'll see here. So we'll start with BayesiaLab. That's where we build the model. That's where we test the model, where we can try out scenarios. Once we're done with that, we upload that network to the BayesiaLab server. But what's very important here is that we're only transmitting the network itself. Now here, in our particular case, we don't have any underlying data, but in other cases, you may have learned your network from potentially sensitive business data. So that underlying data is never being transmitted. So it's only the model, only the relationships that are uploaded to the BayesiaLab web simulator server. And once it's there, you can make it available in two ways, either to the wider world, where you simply publish your network and then anybody can basically look at it and experiment with it, and there are many applications for that. Or in a business case simulation, you will probably only want to share that with people in your company, and then you can set up private and secure web simulator accounts where you give everybody credentials who is supposed to see that model. So, but for the public models, you can simply go online, simulator.bayesialab.com. And you'll see a whole bunch of simulators that other folks, other researchers have published, really in all kinds of domains, from e-commerce simulators to diagnostic measures, a soccer World Cup simulation tool. It's a wide range and it's constantly changing, a great way to become familiar with what other researchers are doing with Bayesian networks. But let's now look at our web simulator. Here you see the final product. I'm going to show you the final product before going back into BayesiaLab and showing you how we actually created that way. That's the objective. On the left, we have our input nodes. You can see the logos that are, or the icons that I have selected. You see the different types of inputs. For instance, for inventory target, I have a drop-down menu because my target state would be in discrete units. I either have an inventory of 7 or 8 and so on. So I have discrete states set for that. Whereas for my standard deviation, for my demand, I have sliders. I can either use the slider to move back and forth, or I can type in a specific value that I have. On the right-hand side is my output. There you see the overall utility with a gauge. That's the visualization I chose, and a corresponding icon. So we'll see how that moves around as we set different values. And now here, this is quite important, surplus and shortage, because that's really very critical. This is basically how often we are have a surplus as opposed to how often we're spot on in terms of our inventory and how often we have a shortage. Because depending on what the cost for oversold versus unsold unit is, that has a huge impact in the utility. And so here I've decided to visualize at least one of these distributions, so stakeholders can see what happens. You know, if we're increasing inventory, if we're decreasing inventory, how does that affect the surplus and shortage distribution? We could show these distributions for any variable we want. So I've just shown here a selection of different visualizations. Also, what's important, we can at any time, or the end user can at any time, bring up the network and therefore see, well, what's the structure here? What's in the background? Now here, the end user can't manipulate that. It's simply a visual, but it allows him or her to understand, well, how are these values calculated? So let me now briefly leave PowerPoint and switch to BayesiaLab. Let's see whether I can manage that switch. Always a bit tricky. Hold on, where is the screen I want to share? Okay, here we go. Momentarily, you should see BayesiaLab, and I've already opened up the network that we defined earlier. And now on the right-hand side, you see all the monitors, but no values are entered yet. So here all the monitors have a uniform distribution. This is basically the starting point where we can now enter our beliefs and then see what these beliefs, what these assumptions do. So let's start. And I would, well, here that's probably the obvious one to start, demand forecast. This is the box, the monitor that is now highlighted in red. And I'm saying my forecast is 5. So that's my belief. And I can set now also a uncertainty that corresponds, and I'm saying 0.5 in terms of standard deviation. I've now set that, or perhaps, yeah, let me leave it at that. Based on these two inputs, you can now see the actual distribution of demand in the monitor at the bottom that is now highlighted in red. So that's what is computed as a result of my input. Okay, now perhaps intuitively you would say, if I have a demand forecast of 5, let me set an inventory target of 5 units. And then also let me set an inventory a fluctuation or uncertainty for that inventory. And here I'm arbitrarily setting 0.25 in standard deviation. So a very narrow distribution. It seems like I feel quite confident about what I am forecasting. So based on that, I would have my surplus shortage distribution on the right, and in the purple box, my overall utility. So, but here I set my specific inventory target based on my guess. I could also leave that task to BayesiaLab. So I will remove the evidence from inventory target and ask BayesiaLab to learn for me what is the optimal target. Now, this should not come as a great surprise that, well, actually it's not 5. It turns out to be 6 because of the distribution of surplus and shortage, even though the demand is 5, given that in our case here, oversold units, unfulfilled demand is very costly. The result is that we should actually have 6. You'll see this little light blue bar among many of the dark blue bars. That tells me 6 is indeed the optimal inventory target. I can try that out. And indeed, with an inventory level of 6, I have an overall utility of 107, as opposed to if I were to go with 5. You can see here now this is a little bit small probably on the screen. And I'm just realizing that sorry, I'm hesitating right now. I just thought for a moment that I was sharing the wrong screen with you, but I think you actually see the correct screen. So we can proceed. So at 4, at the inventory level of 5, we are at 83. If I tried out 7, it would be 96. So indeed, an inventory level of 6 gives us the maximum. Okay. Not particularly exciting so far, close to our estimate. But now I'm changing my uncertainty. I'm changing the standard deviation from for the demand to 2, and also for the inventory fluctuation to 2. So now you see we have a much broader distribution of the demand here at the bottom in the demand monitor. And as a result, we also have potentially have a much broader distribution for surplus and shortage. So let's now relearn the optimal inventory level given these new levels of uncertainty. So let me learn the static policy. And now, as it turns out, the optimal inventory level is 8, or the inventory target is 8. So I can try that out. And here now I have an overall utility of 59. And if I compare that to lesser or higher inventory levels, yeah, it just about 8 is the best. 9 is almost as good. Level of 7, 7 here is quite a bit less. So I can now experiment with this and get a sense of what works. Now, of course, finding a single target is very straightforward, but often there are more variables that we have to decide on. As in the expanded example with economy and first class, now we have to determine 2 levels. And there may be many, many more that we have to simultaneously optimize. That's where this policy learning function is very, very practical, because BayesiaLab can go through all these, each time taking into account all the distributions, working natively with the distributions that we have in this domain and then look for the optimal levels. But now let's leave BayesiaLab, or rather, let's now switch to designing our web simulator. I'm going into the web simulator editor, and there you see the interface that now allows me to define how I want this network to appear, or rather how I want individual nodes to appear in the interface. So here we have inputs. I have already populated several of them. So as inputs, for instance, I've selected inventory target states. I've selected inventory fluctuation, my standard deviation, demand forecast mean, and so on. Cost per unsold unit, cost per oversold unit. I can define here how I want it to appear with a slider, with text, with both. I can determine how the values are simulated. I can determine what image I want to show, and so on. Then for the outputs, I just have two elements. I have the surplus and shortage probability bar, and I have the global utility gauge. That's with the big sigma symbol that I have selected. I can determine the size, I can add further descriptions, and what's very practical here, I can, whatever design choices I make, I can immediately produce a preview. Here with the preview button, I'm not going to do that because that will open up a new window on another monitor that you won't be able to see. But since I'm going to switch to a browser now anyway, you can see the end result, which is just the same. But this is very helpful, so you can go play with different sizes and font sizes and colors until you have the optimal appearance that you like, and then you can upload it and publish it. So, as promised, let me now switch to a browser. So here is now the network that is uploaded. And here I've skipped the process of loading the file. It's really as simple as saving the Bayesian network as an XBL file and then uploading this via the admin panel into your account, from where you can publish it. And for instance, if I go here into my admin panel, oh, I logged out inadvertently. Well, and I don't remember my password, or I have to look that up. That's going to take too long. So I'll just go back. I'm sorry, I should have had that readily available. Let me go back just to the public view. This is how the end user would see my interface. And let's now experiment with it like we did earlier in BayesiaLab. So I can now say, all right, let me plan on an inventory target of 5. Let me set a demand forecast of, let's say, 7, inventory fluctuation 0.5, demand forecast uncertainty 0.7, cost per unsold unit I'm entering 10, and cost per oversold unit 125. Totally arbitrary values, but I'm trying this out. And whenever I enter a value, you can immediately see how the output panel on the right is being updated. You can see the surplus and shortage distribution update, and also my overall utility. It looks like with the demand I specified, I'm always short. I have an issue here with my, this is obviously not a profitable business, so let me increase that to 8, and let's see what's happening. Okay, now our business case seems to be much better. Now our overall utility is positive. So we can experiment with that. As I said, this is highly, highly simplified. There are many more variables that could go in there for which we may have to provide assumptions. And I also referred to scenarios earlier. I could now take scenarios that others have developed. I could load that here and then evaluate that on that basis. This, in fact, has become a very popular feature of BayesiaLab because it's a very good way of sharing your research with end users. And this can be in all kinds of different domains. Marketing mix modeling has been a very popular application, but they're really for anything for which you might build. Couldn't I do all that with Excel and perhaps with a Monte Carlo simulation plugin? Yeah, in this simple case that we have just done, you could have probably achieved something quite similar, but you probably have many more variables that you need to determine, that you need to set, many more levers that you could pull. And with that, if you were, for each level of choice, if you had to simulate thousands of cases to generate simulation or to generate distributions, that computational demand could be just explosive and really be no longer tractable. This would only work really in trivial cases. Whereas with a Bayesian network, you can work natively with distributions. So that is what makes that so attractive. You can immediately work, you can enter distributions, you can see the distributions. You don't have to run 1,000 iterations each time before you can see a distribution. And in BayesiaLab and in Bayesian network, you can go in for any variable at all times and see what the values and what the distributions are. So it's very intuitive, very auditable. This is extremely important in a business context where you want to be able to trace, well, why did we decide it? Why did we just decide certain things? What did we assume? What did we, who assumed what? How did this assumption, the scenario come together? In a Bayesian network, that can be very, very explicit. So, as I said, a more interesting version of this would now be if we had two classes of service. Now, for that, we unfortunately don't have time, but I'll leave that to you as a homework, and I will also give you the solution, actually. So when you go on our website later today, go to the page associated with this webinar, you should see the slides plus the networks that support or that we've gone through just now, both for the single class of service scenario as well as for the two class of service business case. So with that, just a few more concluding things. Now, this was just one tiny snippet of what you can do with Bayesian networks in BayesiaLab. There are so many more applications. A great way to learn about Bayesian networks is to join one of our courses. The next one starts next week in Cape Town, South Africa, our very first course ever in Africa. In February, we'll be in Dubai, then back in the US in March with a course in Washington, D.C., Amsterdam, Singapore, Sydney, Australia, Paris, Seattle, Washington. So you can see every month we're basically in a major city around the world, both with courses, but then also we have very, very popular seminars in addition to our regularly hosted webinars. Now, you can try out all this for yourself. I will share the examples. If you download an evaluation version or a trial version, you will be able to experiment with the examples that we've gone through today. Just a quick note where you can learn more about BayesiaLab or interact with other users. We have an online community forum, and perhaps the best way to get to know and learn about other research with Bayesian networks and BayesiaLab is joining our annual conference. Last year in November, it was in Chicago. This year will be at the North Carolina Biotechnology Center in Durham, North Carolina. great venue, very nice place. Think about joining us. We have already some of the details on our website, and you can also register already. So with that, I'd like to thank you for your time and interest. Please do feel free to reach out with any questions that may have come up throughout my presentation. Reach out to us, connect with us on Twitter, Facebook, LinkedIn, etc. And I'd love to see you again in a future webinar. Thanks again and have a great day.